Hello, today I will be talking to you about Circuits Lab, which is the fourth lab for Physics 2212. Introduction and Purpose. In this lab, we examine circuits using the physics principles of energy conservation, current conservation, and Ohm's law. We know from energy conservation that the overall energy remains the same, and from Ohm's law that voltage, current, resistance are related, and a change in one quantity will result in proportional changes in one or two of the others. We will predict the behavior of circuits containing resistors in series and parallel, and we'll measure them. 1. Series circuits. Experimental setup. We created a simple series circuit using two 1.5 volt batteries, two resistors, and two multimeters as shown in the diagram and picture below. Data and discussion. For current, we expect the current readings to both be around 20 milliamps from Ohm's law, and we obtain an empirical reading of 13.6 and 13.8 milliamps, and this is primarily due to the fact that our batteries were only outputting 2.4 volts rather than 3. If you hook up a voltmeter, when we change a multimeter to voltage mode, the multimeter set to voltage gives us an error reading, and the one still set to current gives a 0 amp reading. This is because the multimeter is essentially a break in the circuit. It technically has really high resistance and theoretically has infinite resistance if we're going for an ideal voltmeter. And this is because they read potential difference. And there wouldn't be a meaningful potential difference if potential difference. So now that we know how to use a voltmeter, we use that to create in parallel with circuit components to measure the potential difference at each around each circuit component. And once we have all of that data, we sum it up, and we can see that it confirms our expectations that a round trip electric potential would be 0, and our results are very close to 0. Um, Calculated resistances, and when we put the voltages around each component and the current around each component, we can calculate the resistance, and they come out to be fairly close to what we expect. The weird one for me is the ammeter is a little bit higher than I expected. I would have expected to have a similar resistance to the wire. All right, on to part 2, resistor capacitor circuits. RC circuit. When a resistor capacitor circuit is created, the light bulb lights up and then fades to nothing. And when we remove the battery from the circuit and connect it again with only the capacitor as the power source, the light bulb lights up again and fades again to no light. The capacitor takes about 3 seconds to charge and 5 to discharge with a 10 ohm light bulb in the simulation. And the capacitor takes about 6 seconds and 9 seconds to charge. Time dependent voltage. So we're doing the same thing, plugging in a battery to the RC circuit, removing it, and then letting the capacitor discharge itself on the light bulb. Now we're taking data of it so we can see the slope of this, and this slope can be used to calculate the time constant RC, which, because we're using an ideal simulation, gives us experimental discussion questions. So I did this lab in real life, and I believe the biggest difference with a simulated ammeter is that it would not contribute any resistance to the circuit, whereas putting in my ammeter, it would have added a slight resistance to it, and we even calculated that it was like 7 ohms, which is very small, but it still changes the current a little bit. And then also that it was much easier to read the simulated ammeter. Conclusion. In this lab, we examined circuits using the physics principles of energy conservation and current conservation. We conducted experiments that showed how voltage, current, and resistance are related. We first measured currents and voltage in a series circuit, and then we measured the charge and discharge times of RC circuits. And through these experiments, we are able to confirm that the conservation of energy is demonstrated by a circuit as we expected, and we observed the relationship V equals IR, which is Ohm's law, holds true.